in the previous chapter. So let's have a look at the basic elements of the SOFC. This, from an engineering perspective, this cell is composed of our electrolyte, which is seen in the center here in green. On either side of the electrolyte, we do have a cathode and we have an anode. Now, we've seen that we have this kind of gas streaming channels basically being surrounded by the cathode. So this, what I called anode gas compartment and cathode gas compartment. And this is basically what is meant with this part here. So through these channels here, our oxidizer is streamed, and respectively down here through these channels, which are like going perpendicular to the other ones, there we stream through our fuel. And this is basically one small cell, and this cell is stacked with multiple others. So here we have an interconnect. An interconnect is basically a separation to our next cell. And here we start stacking again with our anode. Then we have our flat anode, electrolyte, flat cathode, and the secondary part of the cathode again. So we just continue stacking our cell up and downwards. Now, I would like to have a look at each of these elements, and I want to start off with the electrolyte here. The electrolyte has to serve certain requirements in able to qualify to be used as electrolyte in fuel cells. So the electrolyte has to be gas tight, which makes sense because our gas shouldn't just like diffuse through on the other side and not facilitate a fuel crossover. We need a good ionic conductivity. This can be any kind of ionic conductivity. If we look at all fuel cells, we've seen that sometimes carbonate is transported, sometimes hydroxide is transported, sometimes oxide is transported, sometimes protons are transported. So in the specific case of the solid oxide fuel cell, we are of course transporting oxide ions, so O2 minus ions. At the same time, we need a low electronic conductivity. So the electrolyte has to be a good ion conductor, but a bad electronic conductor. Ideally, it's just a simple plain insulator, of course. So by not having any electronic conductivity, we make sure that we do not have any electronic leakage currents, which might compromise the efficiency or operation of our cell. One major economic factor, of course, is always the price of the electrolyte. So we would like to have something cheap. What might seem only obvious at a second glance when you think about the engineering perspective is that we also need a system compatibility. So the electrolyte, of course, also has to match well with interfacial areas with our electrodes, for example. And of course, it has to transport the right ion, to say the very obvious fact here. And two further points are the actual stability. So chemical stability, and this chemical stability has to be the case for both reducing and oxidizing atmospheres, because the electrolyte is in contact with the anode as well as with the cathode. And of course, we also need physical stability as the second stability factor. So we would like that we do have some mechanical integrity, that the electrolyte is not readily breaking or instantly cracking if there is some expansion, for example, in the cell. You might notice, however, that some of these requirements are kind of going in opposite directions. So being gas tight, having a high physical stability, and a low electronic conductivity, these kind of factors are more or less scaling in the direction of having thicker electrolytes. On the other hand, if we think about high ionic conductivity or cheap material costs, we are thinking about rather thin electrolytes. So this is effectively a question of finding a trade-off between these opposing trends. The electrolyte itself is, as I already said, an oxide ion conductor, so oxide O2 minus, and it is provided by vacancies in the crystal. So what does that mean? Let's just assume we have a crystal of our electrolyte. What is a crystal? A crystal is simply an arrangement of cations, so of positively charged ions, and anions, so of negatively charged ions, which repeats itself periodically. And this is exactly what we see here. We have this kind of motif here with anions following in regular distances, and we have cations always in between for anions here. The anion in our case is, of course, the oxide ion, because this is what we want to transport. So how does a crystal structure like this now exhibit suddenly a certain ion conductivity? And this is ensured by so-called vacancies. A vacancy is basically a missing spot of an anion, and I just suggested that here, for example, we have 3 vacancies in our crystal lattice, and what will happen if we offer this crystal lattice now extra anion, which, for example, forms as a product on one of your sides, for example, of your fuel cell. And here you will simply see that the anion will now occupy the vacancy. And as this is working in kind of a caterpillar mechanism that one pushes the next, what you will notice is that once this occupies this vacancy, another anion might fill this vacancy, and another adjacent anion might fill this vacancy now. And by this process, you stepwise ensure the conductivity of ions through the cell. And as you've seen now, we basically are back at our previous pattern, but we transported one anion in the cell, which is this anion here, and we did get something out of this cell here, which was this anion which we kicked out from this place here. So by this, we can, through a resupply of anions on the left side, we can make anions wander through the cell and kick them out on the right side, therefore effectively transporting anions through our crystal lattice. This was a little bit abstract, so now let's have a look how it actually looks on in terms of chemistry. So I told you before that this kind of electrolyte which is used here is yttrium stabilized zirconium oxide. And this kind of structure provides suitable oxide vacancies. And this is due to the simple fact that if we look at the pure zirconium oxide crystal lattice, it has this zirconia in there having a 4+ charge, because this O2, these are both oxide ions, so having each two negative charges. So the zirconia has a +4 charge. We now add yttrium to this structure, and our yttrium or yttrium oxide now again has oxygens which are oxide ions, so 2-, giving us here 3 times 2-, or overall of 6- charges. And we have 2 yttrium, so that means each of our yttrium will have 3 positive charges. So now by substituting part of our zirconia here, for example, this zirconia here on this outer side with yttrium, as you see it down here in this combined structure now, as we combine it, we have to kick out some oxygen out of the structure. And this is because our yttrium has a smaller charge than the zirconia. And due to the smaller charge, we have to get rid of excess negative charge, of course. And the only thing what we can do for this purpose is to kick out oxygen of the structure. So this is the so-called YSZ, the yttria stabilized zirconia, which crystallizes in a cubic fluoride structure. This yttrium stabilized zirconia oxide is very much the established material for this kind of fuel cell, for this SOFC. It allows the tailoring of mechanical stability due to the fact that you can vary your yttrium part in there. You can either dope more yttrium in or reduce the compound's yttrium richness. It offers chemical stability in oxidizing and reducing atmosphere. This is very important. And it has a pretty much established manufacturing process as it's pretty much known for these kind of cells. The conductivity can actually be further optimized with other elements, for example, scandium. So scandium can also be doped into the structure. However, the big drawback about this is that scandium is very expensive. So this is usually not an economical process to dope it with scandium. One issue which arises on the engineering level is that the YZ has limited compatibility with the cathode materials. So here we notice some kind of degradation behavior. And also, why is that? And this is why we were using scandium in the first place, is that we pretty much have a mediocre ionic conductivity. So to obtain sufficiently high ion conductivity, we need very thin layers of the material, or we need very high temperatures, both of which are kind of a risk. First of all, a safety hazard, of course, because high temperature makes the cell, in principle, more risky to run. Also, thin layers make it more prone to cell failure, for example, but also due to the regard that high temperatures have to be reached, so you have to invest a lot of energy to run this cell at the high temperatures. Of course, at some point it will be self-sustaining. So this is in principle, again, this equation what I gave you. So you have zirconia here with the zirconium having a +4 charge. And if you put yttrium in there, you will get something like zirconia yttrium oxide here. So the lack of positive charge arises due to replacement of zirconia with yttrium 3+, and this can only be compensated by a removal of oxygen in this kind of system. So what you effectively have here is basically a number which is a little bit lower than 2. Another electrolyte considered to be used in SOFCs is so-called samarium or gadolinium doped cerium oxide, or GCO as an abbreviation. This material has a higher ionic conductivity, and the great thing about it is that it can, even at lower temperatures, be significantly better than the YSZ as we've seen it before. Also, the material is pretty much compatible with various cathode types. What we've seen is also of great importance, because once you have a mismatch with a anode or a cathode in your system, you will also face more drawbacks and additional degradation, what we will talk about later on. Unfortunately, the material has a lower mechanical stability than our YSZ, and the lattice parameters change. So what are the lattice parameters? The lattice parameters are basically the dimensions of your unit cell in your crystal structure. So you can imagine that this material is being comprised of a lot of unit cells. And if each of these unit cells grow along a certain axis, then the material also expands as a whole. And this can lead to various problems in your cell, because once you have a volume expansion and volume shrinkage, you might lose contacts in some parts. This shrinking and expansion behavior is additionally aggravated by the fact that cerium can undergo a reduction reaction in a reducing atmosphere. So we've noted it as a requirement before that the material has to have stability in oxidative as well as in reductive environments. And here you can basically facilitate the reaction of cerium 4+ being reduced by an electron to cerium 3+. Additionally, the material has a high electronic conductivity. So we've learned that we want ionic conductivity of the electrolyte and ideally little or ideally no electronic conductivity. As the material has a certain electronic conductivity, we typically have certain leakage currents which hamper the efficiency of our fuel cell. The effect is, however, overcompensated by a higher ionic conductivity for this kind of system. So the material is in fact interesting for low temperature applications.